Hi, everyone. So today we're going to learn how to judge whether a predictive model is doing a good job or not. In many situations, a model gives us a number, a score, or a forecast. Our job is to decide whether that result is accurate enough to trust and useful enough to support us making a decision. Think about a weather forecast. The forecast gives you a prediction, but you still want to know whether it's reliable. A predictive model works the same way. It gives us an estimate, and then we evaluate how well that estimate matches what's really happening. So, throughout this lesson, keep in mind, how do we know whether a model is good? Everything we cover today will help us answer that question. So let's get started. Today we're going to be evaluating predictive models. So by the end of this lesson, you should be able to explain what a predictive model is, what it does, and you should be able to identify the differences between an outcome and a predictor. So your dependent and independent variables. Describe simple and multilinear regression. Explain training data and validation data. Understand how a model makes predictions and use R squared, MAE, RMSE to evaluate performance. You should also be able to compare models in a real way. That means you're going to look at more than one metric and you're going to think about how accurate the model is and decide which model fits the situation best. So, I want you to learn some vocabulary today, but my main goal is for you to understand the ideas well enough so that you can explain them to someone else and use them to evaluate a model. So, why does this even matter? Why do we care? Because people and organizations use data to make decisions about the future all the time. A business may want to estimate a future sales. A school may want to predict whether a student will be successful or not. A hospital may want to estimate how long a patient will stay. A company may want to predict the shipping time or product demand. In each of these cases, the past data is used to generate a pattern, and those patterns help us estimate what's likely to happen next. That makes predictive models very useful because they help turn the data that we have into action. We can make a decision from it. So, a model helps us make a better choice. So that's why we evaluate our models so much. Anyone, before anyone can rely on a prediction, they need to be confident that the model actually performs well. So, what is it? What is a predictive model? A predictive model is just a tool uses information that we already know to estimate an outcome or something that we want to know. Let's use a simple example. Imagine we want to estimate the selling price of a car. We already know how old the car is, the year that it came out, the mileage on the car, and we know the brand. A predictive model studies the patterns from past data and uses those facts that we already know to estimate the price that we're likely to be able to sell that car for. The same idea works in many areas. A model can estimate price, time, demand, score, cost, or risk. Um, the model takes in information and it looks for patterns and produces an estimate. So when you hear the phrase predictive model, think of a system that turns known facts into an informed estimate. So an example you see on the screen, when you're looking at maybe pricing a house, maybe you have the area of the house or the square footage, and you have the number of bedrooms. Then you have a model that'll generate something called an intercept and coefficients. And then it'll predict your expected outcome, which would be something like your sales. So you have your input variables, which are your independent variables, and you use those to put those into a model to predict your outcome variable or your dependent variable, which is sometimes called. So the process, and this is something that I want you guys to try to remember, learn, use it like the back of, just remember it. This is the process you're going to follow every time, and each step matters. The first step of a predictive model is define your problem. You need to be clear about what you're trying to predict. And next, what data do you have? You need to choose your variables. Look at your data and figure out, what are you trying to predict? What is your outcome or your dependent variable? What are your input variables? What are your independent variables? What are you going to use to figure out the answer to your problem? Then you're going to take the data and you're going to split it. What that means is we're going to take our data and we're going to use some of it for training and some of it for validating our data. We're going to take a sample of our data, and then we're going to use it to train and validate our model. And the next thing we're going to do is we're going to build our model. And I'm going to show you all how to do all of this today in Excel. Then we generate our predictions. We compare what we generated, our actual values. Then we evaluate with metrics. And after that, we choose which model is the best. Um, it's a sequence, and we're going to do it in the same sequence every single time. And this is the pattern or the process or the workflow that we're going to follow every time that we're going through and we're building a model. We have a data and we need to make a prediction on that data. This is our predictive modeling process that we are going to follow. Okay, now we have our problem. Next thing we do is we try to figure out our outcome variables and our predictive variables. We're going to separate it into two things: outcome variable and our predictor value. The outcome is also called your dependent variable, and your predictor value variables, it's also called your input variables sometimes, or they're called your independent variables. So here I'm going to use the term outcome variable and predictor variables, but remember they do have different terminology depending on what room you're in. So the outcome variable, that's the result we want to estimate. It's the target. If we are estimating the house price, then the price is the outcome. If we're estimating a test score, then the test score is the outcome. Now, predictive variables, those are our inputs that help us explain the outcome. And if we're predicting a house price, the predictors might include the size of the house, the age of the house, the location, number of bedrooms, number of bathrooms. And if we're predicting something like an exam score, the predictors might include something like study time, attendance, homework completion. A simple way to remember this is that predictors go in and the outcome comes out. Now, regression, that sounds like a big word. So, regression, that's the method that we're going to use today to predict a numeric outcome. Regression is used when your outcome is a number. There's different types of models out there, but today we're going to focus on regression. So when the result we care about is a number, regression is usually the choice that we use for our model type. Examples of numeric outcomes include things like price, revenue, time, distance, cost, or score. They're numbers that we're trying to predict. And regression, it helps us understand how the outcomes change as one or more of your predictors change. You can picture regression as a tool for finding a pattern in the data. If one variable tends to rise when another rises, regression helps capture that relationship so we can use it to estimate new values. So when you hear the word regression, think about predicting number by learning a pattern from the data. So regression is used when the outcome is a number. All right. So, in particular, we're going to focus on two types of regression today. We're going to first focus on simple linear regression, and that uses one predictor to estimate one numeric outcome. Suppose we want to estimate a person's test score using only the hour study. That's a simple linear regression because we have one predictor, one independent variable, one input, um, which is our study, and one outcome, which is the test score. So this kind of model, it's useful because number one, it's easy to understand. And number two, it's easy to visualize. We can plot the data on a graph like what you see here, um, and draw a line that shows the general pattern, which is usually called the best fit line. Simple linear regression, it's a good starting point because it shows how one variable relates to the outcome in a direct way. So for the example on the screen, you see as the predictor value increases, the outcome increases. So that's the relation this chart shows. Uh, if the slope was going downward, that would mean that as the predictor increases, the output decreases. Remember that in data analysis is all about explaining your results. So what you see, remember, you need to communicate it. So an upward line, an upward slope would mean that as the predictor increases, the outcome increases here. A downward slope, as the predictor increases, the outcome decreases. Now, next we have multiple linear regression, and that's where you have many predictors or many inputs or multiple independent variables. Multilinear regression uses more than one predictor to estimate one numeric outcome. Let's go back to the test score example. We might use our study attendance and homework completion together to estimate the score. Each predictor contributes information and the model combines them to make one prediction. So we use this because many real world outcomes depend on more than one factor. A single variable usually does not tell the whole story. So multi-regression helps us build the fuller picture by using several inputs at the same time to make our prediction or to get our outcome. So why do we use more than one model? Comparing more than one model helps us avoid choosing a model just because it looks more detailed. A simple model may be easier to explain and easier to use. A more complex model may capture more information. The only way to know which one serves the job better is to compare them. Think about two routes to the same destination. If you use the GPS in your car, my car, I have Google Maps, I have the Apple Maps on my phone, and they give me different directions and different times that they estimate for my destination. I also have my in-car navigation system, which gives me a third option. And from using my experience, I tend to go with Google Maps because it's usually more up to date and gets me there without having any issues. But I do have the options. So think about you have two routes to a destination, which I have when I use my different maps in my car. One route is short and direct, and the other route has more turns and looks more advanced on the map. The better route is the one that gets you where you need to go more effectively. Models work the same way. The better model is the one that performs better for the purpose we care about. For me, when I'm driving, if I'm in a new area, I'm usually going to choose the route that has the fewest amount of turns because for me, that's what's most important. If it is somewhere where I'm familiar with the area, and this is what's important to me when I'm making my decision, every case is going to be different. But if I'm in an area I know, I'm usually going to use the map that has the shortest time because I'm just trying to get there fast and I generally know how to get there. So it's not just about which one produces the type of data you want. You have to think about your scenario and your business problem and what is important for that problem. So, though a model may perform better, it may not be the best model depending on your situation. You have to think about what matters most. So, the next thing we have to do is we have to sample our data. In many situations, we work with really large data sets, and sampling helps us create a manageable group of cases to build our model and to test our model. Sampling is important because the cases we choose shape what the model learns for. If the sample is unbalanced or biased, the model may learn patterns that don't really represent the larger data set. So, a fair sample gives the model a better chance to learn patterns that actually reflect the broader group. So, sampling, it's a part of building a trustworthy model. It should represent the data well. So, random sampling, which is what we're going to do today, means that each case has a fair chance to be selected. It helps us reduce bias in our data. It supports a more balanced sample. So, here's a simple example. Imagine a full jar of red, blue, and green marbles. And if you only grab from the top, you may get too many of one color. If you mix the jar first, then pick randomly, you have a better chance of getting a fair mix. The same idea applies to data. Random sampling helps us avoid building a sample that's tilted in one direction, and this is important because fair sampling supports a fair model evaluation. It's kind of like if we're trying to get someone's opinion and we go to just one neighborhood to conduct a survey. Well, the people in that neighborhood, they're usually kind of alike. They may have the same income levels, maybe the same demographics, and you usually get the same sort of answers. And to have better survey results, you want to be able to have different types of people answer your surveys. You don't want the same type to have the same type of demographic because you want your answers to kind of represent the entire population and not just the answers of a select few. And that is why we try to generate a random sample of our data. So, in our random data, we have what's called training data and validation data. Training data is the part of the data set used to build the model. This is where the model learns the pattern between predictors and the outcome. In regression, this is where the model learns how the changes in predictors connect to changes in the result. You can think of training data as the learning phase. The model studies these cases and develops the relationship it will later use to make predictions. So, training data is important because every model has to learn from something. So, then we have the validation data. And validation data, it's a separate set of cases that we use to test how well our model that we created generally performs on the data it has not seen before. The step is important because a model can look strong on the data it learned from. Validation data gives us a more honest test. A helpful comparison is practice versus the real test. So, um, something may perform well. It's like a student who is studying. When you're studying, you may perform well on the questions that you actually studied for, but a good sign of learning is doing well on new questions on the same topic. So, validation, it gives us the kind of check that like a test in school would. That's why validation is such an important part of model evaluation. It's test. It's where we test how our model performs. Now, a static holdout method. This is how we're going to break out our data, our random data, into our random sample of our data, into our training data and our validation data. The static holdout method means we split our data once into two parts. One part is used for training, and the other part is held back for validation. And the common method of doing this is 70% of our sample data is used for training, and 30% is used for validation. The exact numbers can vary, but the purpose is the same. One part teaches the model, the training data, and the other part tests the model. That's the validation data. This method is popular because it's simple and easy to follow. It gives us a clear boundary between learning and testing. So it helps us be honest and fair about how we're evaluating our model's performance. So, why is validation important? Um, Validation is important because a good model needs to perform well on new cases. A model can look excellent on training data simply because it's already studied those cases. Validation shows how the model behaves when it has to work with unfamiliar data. So that's the real challenge in the real world. Models are used on future or unseen cases. So the validation result gives us stronger evidence about whether the model will actually help when it's used. When you compare models, validation results, they need your attention. You have to pay attention to your validation results. Now, overfitting happens when a model learns the training data too closely and performs poorly on new cases. In that situation, the model has captured a lot of small details from the training data, including noise that doesn't generalize well. And the result is a model that looks strong during training but loses strength during validation. A simple analogy is memorizing exact answers without understanding the topic. So that may work on repeated questions, but the process doesn't work when the questions change. So overfitting is one reason validation is really important. Validation helps us see whether the model learned a real pattern or just memorized the training set too closely. So, how does a model make a prediction? A model makes a prediction by taking the input values, applying the pattern it learned from the data to predict something. For example, suppose a model learned that more study time and better attendance are linked to higher exam scores. If we enter a new student's study time and attendance, the model uses those inputs to estimate the student's score. So the important part is that the prediction comes from the learned relationship. The model has already studied the past cases and now uses that learning to estimate what's going to happen when something new comes in. So a prediction is the model's best estimate based on the information it was given. So to evaluate a model, we compare the predicted values to actual values. A predicted value is the estimate produced by the model. An actual value is the real result that happened. So when the prediction is close to the actual value, the model is doing a better job. Suppose a model predicts the selling price of um, a house and the predicted value is 405,000 and the actual selling price turns out to be 420,000 like we see in the example here. The model was close but not exact. And um, in this case, the predicted error is $15,000. Now, depending on your numbers, and what you're working with, this could be a good number, it could be a bad number. But when you repeatedly do comparisons of the predicted and the actual results, you get evidence that we use to judge how a model performs. So, what is a predicted error? Predicted error is going to be the difference between the actual value and your predicted value. If the prediction is close to the real result, the error is small. If the prediction is far away from the real result, then the error is large. Prediction error is important because it tells us how far off the model tends to be. A good model keeps the differences really small. So, whenever you hear the word error in model evaluation, think about the size of the miss. It doesn't mean that something actually went wrong. It can if the numbers are far away, but it means the size that we're off of the actual results. Um, When we evaluate a model, we usually have many validation cases. Looking at each prediction one by one is not enough. We need summary measures that show the overall performance. Evaluation metrics gives us that summary, and they help us compare models in a consistent way. These metrics let us answer questions like how much of the pattern did the model capture? How large are the errors on average? How much do large misses matter? So, we're going to focus on the three common metrics, which are R squared, MAE, and RMSE. And I'm going to go over each one of those. So R squared. R squared is going to tell us how much of a variation in the outcome is explained by the model. If R squared is 0.8084, that means the model explains about 80% of the variation of the outcome. Higher values for the R squared usually mean the model captures more of the overall pattern. This makes R squared important because it gives us a quick view of the model fit. You're going to hear that a lot. Fit, that word fit. It tells us how much of what we see in the outcome is being explained by the predictors in the model. So R squared it's helpful, but later we'll see why it should be used with other metrics. Remember that for R squared, the key thing I want you to remember that the higher the value, the better. So you want your R squared to be high. So the next thing we have is MAE. MAE stands for the mean absolute error. MAE tells us the average size of the model's errors using the original units of the outcome. So outcome is measured in dollars, MAE is in dollars. And if the outcome is measured in minutes, MAE is in minutes. For example, if MAE is 18, the model misses the true value by about 18 units on average. That makes MAE easy to explain because it answers a very specific question on average. How far off is the model? And for MAE, you're going to want that number to be lower. MAE, you want a lower number. So when you read MAE, think about three things: interpretation, scale, and context. Interpretation is straightforward because MAE uses the original units. So if you're predicting your price in dollars, MAE, the difference, average difference is going to be in dollars. If you're measuring a distance in miles or predicting a distance in miles, MAE is going to be in miles also. Now, scale is important because an MAE of 10 may be tiny in one problem, but it may be large in another. So context matters because the importance of the error depends on the situation. Um, MAE is also less affected by a few large mistakes. Um, by a it's also less affected by largest mistakes than the next one we're going to look at, which is RMSE. And that makes MAE useful, a useful measure when you want a steady view of the average miss size. Um, it's 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 a good tool. MAE is a good tool for understanding a typical error. What is usually likely to be the error? How far off are our predictions? Usually, on average, how far off are our predictions? So the last metric we're going to look at is RMSE. It stands for root mean squared error. It also measures the error in the original units, but it gives more weight to larger mistakes. That means it reacts more strongly when a model has some big misses. For example, if a model usually performs well, but occasionally makes large errors, RMSE is going to reflect that more sharply than MAE. This makes RMSE um, it's useful in situations where large errors are especially costly or risky. And for root mean squared error, RMSE, you're going to look for a lower number. Lower is better. So for R squared, you want a higher number. For MAE and RMSE, you're looking for lower numbers. Now, when you read RMSE, pay close attention to what it's telling you about your large misses, your large mistakes, or your large errors. Because RMSE gives extra weight to bigger errors. It helps reveal whether a model has a few predictions that miss badly. Like MAE, RMSE, it's going to use the original units of the um, of your outcome. And so it's easy to connect to the real problem. The difference is that RMSE places more importance on large misses. So it's value when you really want to see when large mistakes in your model, when those large mistakes matter. So you can't just use one thing to figure out your best model. You kind of have to use your best judgment and understand what these three metrics are doing. R squared, it gives us useful information, but it doesn't tell us the whole story. It tells us how much variation the model explains, but it does not tell us the size of the errors in real units. A model can have a good R squared and still make prediction errors that are too large for the situation. Remember, context matters. Um, so that's why we also look at error metrics. These measures show how closely the model's predictions are to actual values. And you need the complete evaluation, both fit and error, to make a decision. So you're going to look at all three of these things together to make a decision. So MAE and RMSE, they're going to add information that R can't provide by itself. R squared tells us how much the overall pattern the model explains. MAE tells us the average size of the miss. RMSE tells us how strongly big misses affect the model. And together, we're going to get the bigger picture. It's going to help us move from a general sense of fit to a more detailed understanding of prediction. And that's why model evaluation works best when we look at more than one metric. Okay, so again, R squared, it's going to answer the fit question. And MAE is going to answer an average error question. And RMSE is going to answer your big miss question. How are our big errors affecting our predictions? And the combination is going to help us make a better judgment on which model is better instead of relying on just one of these metrics. So, sometimes model comparison is straightforward and it's easy. And that happens when one model has a higher R squared and the lower error values. In that case, The measures are pointing in the same direction. One model explains more variation and also makes smaller mistakes. Now, when this happens, the decision is easier because the evidence supports the same choice across multiple measures. This is the simplest model comparison situation. So in this case, you'll see that model A, it has a higher R squared, it has a lower MAE, and it has a lower RMSE in this case. So in this case, model A would be the better choice. But sometimes model comparison is less clear. One model may have a higher R squared, while another model has a lower MAE or RMSE. That means the metrics disagree. And that's a normal part of analysis. It happens. And this is where your judgment comes in. So, this tells us we need to think more carefully about the purpose of the model. If large misses are costly, RMSE may deserve more attention. If typical error matters most, MAE may be more important. So, if capturing the overall pattern matters, R squared may carry more weight. So, this is where your judgment comes in and becomes a part of the evaluation process. And when you're doing these analyses and you're making these decisions and you're generating a report, don't just pick model A and model B. You need to document why you chose model A, model B. So in this case, model A has a, well, in both of these cases, the R is better, but the MAE and the RMSE, they're both higher. Um, our model B has the lower values for MAE and RMSE. So, what's more important for your particular case is kind of like when I'm choosing which one of my which uh when I'm using my car map and I'm trying to figure out which map to use, and I told you that sometimes my time matters, sometimes the actual path matters. If I'm choosing something where the actual path matters, I would choose the one with with the higher R squared. I would choose model A. But if I'm looking at time or distance, I would choose the ones with the lower errors. So I would choose model B in this case. But if I'm doing an analysis, I would say why. And my reason would be is I chose model A because model accuracy is more important to me. I chose model B because I don't want to make as many mistakes. And that's simple. That's my explanation of why I chose it. Your choice may be different, but you need to document why. Whenever you make a decision in any analysis, you need to document why you made those decisions. So, choosing a better model means looking at the full set of evidence. We want to consider fit, the average area, the effect of the larger misses, and the purpose of the analysis. We also want to think about how the model will be used. For some situations, a slightly simpler model may be the better choice because it's easier to explain and it still performs well. In other situations, a more detailed model may be worth it because the improvement in accuracy matters in that case. So the choice comes from matching the model performance to its purpose. and you need to look at all three. You need to look at R squared, you need to look at MAE, and you need to look at RMSE. Figure out what are your trade-offs. What are you going to lose between the two models? For example, in my navigation, I may go the route that has fewer turns, but it may take me longer to get there due to traffic or something, some reason. But I'm new to the city. I don't want to make all those turns. I just want to get there. But in another case, I need to get to an event. I'm in an area I know, and I know the turns. I just need to get there quickly. So it really depends on your context, your business, um, your your choices, your purpose of the model when you're trying to figure out the best model to use. What is your end goal? So, you need to ask three questions. What decision is the model supporting? How costly are the mistakes? And is the added complexity worth it? And the answers to these will guide your final choice. Business need means asking what the model is supposed to support. And error impact means thinking about what happens when the model is wrong. Um, think about your business. If you're working in healthcare and you're making decisions, the model being wrong is a very bad thing, usually. So think about your business needs. And model complexity means asking whether added detail truly improves the model enough to justify the extra complication. And if two models perform similarly, if one is much easier to explain and maintain, that may be the better choice. If one reduces costly mistakes, that may justify adding some complexity. But the best model is the one that serves the decision the best, that solves the business need the best. So, there are several mistakes analysts need to look out for. One mistake is relying on only one metric. Another is paying attention to only the stronger model. And another is assuming that more predictors always creates a better model. So a model mistake is creating a strong fit number as a whole story. So, good model evaluation comes from looking at the evidence from multiple angles. We're going to listen to all sides of the story and make our decision from all the data that we have and not just one of our metrics. So, you need to, one thing new analysts do is they want to get it done quickly, but I'm going to ask you to slow down. Look at your numbers. Look at all three of your metrics. And what do those numbers mean? Look at your assumptions and make decisions based on all the information you have, not just one side of the story. So think of yourself as the judge in a court case. Um, and you have your defendant and you have your prosecution. You have two sides, and you have to listen to both sides to make a decision. And you need all the information from both sides to make that final decision. So next we're going to do is we're going to do a demo. And I'm going to walk you through a predictive modeling workflow. And we're going to look at the data. We're going to split the data. We're going into training and validation sets. We're going to build the model. We're going to generate predictions and compare the predictions to actual values. And then we're going to use our evaluation metrics to judge the performance. And as you watch, pay attention to the order of steps, and each step is going to build on the one before. The order is what makes evaluation trustworthy. So, let me pull up my data. Just a second here. All right. So this is my data that we're going to be working with. And this is my data that we're going to be working with. And if you look at it, we're looking at the sale prices of houses. And I have 5 variables here. So the first thing we do is we have our problem. We're trying to figure out how these variables affect the price. So how these variables, how the area, bedrooms, bathrooms, and the stories affect the sales price of the house. Now, we have to figure out which ones are outcome variable and which ones are our income variables. So here, outcome. What are we trying to predict? We are trying to predict the price. So we have our actual values and we're going to use our input. Well, go back to price. Price is going to be our dependent variable because it's dependent on all these other variables. And then we have our independent variables are predictor values. These are going to be used to predict what the price is. So remember, we need to look at our data. So the first thing we're going to do is we're going to take our data and we're going to randomize it. So, and I'm going to show you how to do that. So I'm going to create a column here and I am going to call it random. Well, if my keyboard will actually type, I'm going to call it random. Well, that's great. Okay, let's try this. I'm going to call it random ID, okay? And then I am going to put in an equation and we're going to use the rand function to do that in Excel. I'm going to go back because I hit enter and we don't want that. So and I hit enter. Now, I am going to fill this down into all the other rows in my data set. So, and just FYI, I did skip a cleaning step for this data. Um, So one thing you're going to do with your data, you're going to look at your data and you're going to make sure that there are no null values. This is just a demo. That's already been done in this case. And I have data in all of my columns and the data is good for all of the columns that I have here. But I have this random values that were generated, just random numbers. And notice that if I hit enter on this if I were to do something, these numbers just change because it's a formula. It's giving me a random number. And if I were to take this data in these columns and I were to sort the data by the random column from smallest to largest, notice it didn't really sort because the values in the random column are still random. That formula is still there. So my sort didn't really work because it's generated new random numbers. So in order for me to have real values, I'm going to replace this with the actual value instead of the formula so my random number doesn't keep changing. So right now I have this formula in here, but every time I do something, the number changes. Do you see that? Did you see how that number changed? So what I am going to do, if I click there and click off, all of my numbers change. It's generating a new random number. But what I'm going to do is I am going to select this whole column. I'm going to right click and I am going to copy. And then I'm going to right click again and I am going to paste special, or right here, I'm going to paste the values. Okay. And when I do that, it actually puts numbers into this column, static numbers. So the numbers aren't always changing. I get what I get. And after I have the static numbers here, then I'm going to sort the columns. So I'm going to select all of my data. Okay. I'm going to select all of my data, and then I'm going to go to sort. And I'm going to sort my random ID by smallest to largest. Okay. And notice that when I click things, the numbers aren't changing and I have my data from smallest to largest and the numbers aren't changing. And that's why it's important to actually after you create your random numbers, you want to you want to actually use the numbers that were created and not just the random um, equation. Because if you keep the formula in there, the function in there, the numbers in this column will continue to change. Okay, so now the reason why we did this was because we generated a random number and we sorted it so that it shuffled our data fairly. It just randomly shuffled our data. And then by sorting the random column, the rows they got mixed up in a way that reduced bias. Um, and this is important because we want a sample to represent the larger data set as fairly as possible. All right. So now what I'm going to do is I am going to create a sample data set for this. And the sample set is what we're going to use for our training and our validation data. So this is my data here. And I have a total of 200 rows in my data. So it goes down to 201, row 201 because I do have a header row. But I am going to take the first 100 rows of data and I am going to um, create my training data from that. So I am going to take the header and the first 100 rows here, and I am going to copy it. I'm going to put it in a new tab or a new sheet, and I'm going to paste it in. And notice that I have 100 rows of data, but I have 101 rows here because I had to include the header row. So the header row is not a data row. So in order to get 100 observations or 100 rows of data, I'll end up with 101 rows in here because one row is actually my header and not data. Okay, so I am going to name this my training data. Okay, so the next thing I'm going to do is I'm going to create my validation data from my sample data. So I'm going to come here. I'm going to select the rest of the data. Let me change that. That was a little off. Um, this was not my training data that I created. I apologize for that. This was my 100 rows of sample data. So this is my original data here, and this is my random sample. That is not my training data. That is my random sample. Okay, so the next thing I'm going to do is I'm going to create my sample data, my training data from my sample data. And to do that, I am going to use the 70-30 split. So for my 100 rows, I am going to take the first 70 rows of data and I'm going to make that into my training data. Remember that the training data is what I'm going to use to build my model. So I'm going to come here. I'm on the random sample. This is the random sample I took from my full data set. And I am going to take the first 70 records. Okay. And it's going to be 71 because I'm copying the header row. And I'm going to do Control C. And I'm going to put it into a new sheet and Control V that in there. And I'm going to turn this one into my training data. And remember to name your tabs or your sheets properly. Whoever you're giving your analysis to needs to be able to know what is what. So when I create a new sheet and it's called something like sheet 3, that's not telling me anything. So let me delete that one. So remember to name your sheets properly. So the next thing I'm going to do is create a validation set from my data. So I'm going to do it a little differently. I'm going to copy everything from my random sample, Control C, into a new sheet and Control V. And then here, I'm just going to delete 70 rows of data because I want the rest of my data. So I'm going to come down to row 71 and I am going to delete this. And delete. All right. And I'm going to shift those cells up. All right. And so that leaves us with 30 rows of data. You notice I'm on row 31. That's because I didn't delete the header row because I just deleted the first 70 rows because they're organized and ordered and I know that the data is the bottom set. I was looking for the bottom 30 rows in our data. And the next thing I'm going to do is I am going to name this validation data. So I like my sheets to be in order, so I'm going to move this one to the end. Okay, so now I have my original data set here, which is called sample data. I have the random sample that I created. I have the training data, and I have validation. So now, remember that training is going to be used to build the model. And the validation is going to be used to test the model. So the next thing I'm going to do is I'm going to run a simple linear regression. And the way I'm going to do that is I'm going to go to my training data because that's what we use to train the model. To do a simple linear regression, I'm going to run it on the area, which is kind of like the square footage of the house. And the way I do that, I am going to go to this, I'm going to go to the data tab, and I have this data analysis add in here tool here that's been added in, and I am going to click the data analysis tool. Notice I have a pop-up and it says it has different types of analyses that you can actually create. And I am going to do a regression. And I click regression and I click OK. So the next thing I'm going to do is I am going to, when you start off, this X and Y, they may be blank. I'm going to clear those out because I want to make sure that everything is correct. So my Y, I mean, yeah, my Y, that is going to be my outcome variable. So I am going to select everything, all of my data in my 70 rows of data in my price column. And I put it in the wrong place. So I'm going to select the Y column here, and then I'm going to select all of the data that is in my price column. And it populates the values or the locations of those values here. Now, this is where I choose my independent variables, what I'm going to use to predict. And that's going to be my X range. And so I click in this X column, and then I'm going to select all of the values in this column. And you notice it has all of the values, B1 through B71. I'm going to make sure I choose labels here because I do have my header row there. So there are labels, okay? I want things to go into a new worksheet, and my worksheet, this is going to be blank, but my worksheet is going to be called, in this case, I want simple regression model. And I click OK. And voila! We have a simple regression model sheet that was created, and this is my model output. So I'm going to click on it just so that you can see the different values. And let's talk about what we see here. We may not go over everything, but we're going to go over most of what we see here. So first thing we're going to see are the multiple R. Um, the first item is going to be the multiple R, which is here. And that's the correlation between the actual values and the predicted values. It tells us um, how closely the model's predictions line up with the real data. The value ranges from 0 to 1, and we're looking at this one here. Highlight them both. It's going to range from 0 to 1, and a value closer to 1 means that there's a closer the relationship between the variables is stronger. So in this example, multiple R is about 0.99, which tells us the model has a very strong positive relationship between the predicted price and the actual price. Now, R squared. This is what we're interested in for our metrics, okay? This is one of the most important numbers on the screen. R squared tells us how much of the variation in the outcome is explained by the model. So here, the outcome, or our dependent variable, is price. So if R squared is about 98 If R squared is here, it's not about 98%. Um, that means that the model explains about 0.9769% of the variation in price from our model. This is a very high value, so area is doing a good job of explaining the price in this sample. So next we have the adjusted R squared. That's here. And this is it's a slightly more careful version of R squared. It adjusts for the number of predictors in the model. And in a simple regression like this one, R squared and adjusted R are usually very close. In a multiple regression, which we'll look at next, this number becomes more important because it helps us judge whether extra predictors are actually improving the model in a meaningful way. And then we have the standard error, and it gives us a sense of the typical prediction. Um, the typical prediction error around the regression line. Think of it as a rough measure of how spread out the actual prices are around the model's predicted prices. Smaller values are better because they mean the model's predictions are staying closer to the real values. And next we have observations. We had 70 rows in our data that we used in our training data, and this number matches that. So now let's move to the ANOVA section, and the F value, it's gonna measure the overall strength of the regression model. We're not going to be using that just yet. And it compares the amount of variation explained by the model to the amount left unexplained. A larger F value usually means the model is doing a good job. The more important value is the significance of F. That tells us whether the model is statistically significant. Remember the word significant when you're doing an analysis. Only put that word in your analysis if you're talking about significance, okay? I know it's a general word, but in the analytic world, only use the word significance if you're talking about the actual significance, okay? About something being statistically significant. So, in plain language, what this significance F means, it helps answer the question, does the model explain the outcome well enough that the relationship is unlikely to be due to random chance. So here the value is extremely small, which tells us overall that the model is significantly, statistically significant. So now let's move to the coefficients table, and this is what we're going to be using. Today, the main things we're going to be using are this intercept and the area coefficients. So the first row is the intercept, this row here. And this is the predicted starting area when area equals 0. In real business terms, zero area may not be realistic. And as far as a home, you're never going to have zero area. Well, let me change that. You might if like it's a home and you're just selling land, I guess. But in general, the zero value for something, it may not be realistic. So the intercept is usually more useful as part of the equation than as a standalone business insight, okay? So this isn't accurate as a business insight. Still, it's necessary because it's part of your full prediction formula. And the next row is area. This is the area variable. That is our independent variable that we use in our model. Um, that's our predictor. And the coefficient for area, this value here, it tells us how much predicted price changes when the area increases by 1 unit. In this case, as the area increases, usually the price increases by $174. That's based on this model. That means that each additional unit of the area predicted price increases by $174.03 um, based on this model. Now, if you're looking at someone else's model, I want you to know that these numbers are going to be different because they use a different testing sample because they randomize their data to get their training. I'm sorry, they have a they have different training data because they use a different random set. So these numbers will be different every time, but they should be close every time you run your analysis. So we're going to look at these other values, but for what we're doing today, the most important things on here that we're going to look at are these coefficients here and this R squared here. And we're going to use these coefficients to calculate our MAE and our RMSE. So we'll do that a little bit later, but I still want to talk about the other values that you see here. So next we see the standard error column for the coefficient, and this tells us how much uncertainty there is around the coefficient estimate. Smaller standard errors mean the estimate is more stable. So just so you know. The t-stat, it's going to show how large the coefficient is relative to its standard error. A larger absolute t-value usually means the predictor is contributing more strongly to the model. And then we have the p-value, which it's one of the most important values in this table, and it tells us whether the predictor is statistically significant. Notice it's the same as value here. So this is the p-value. Um, a very small p-value means that the predictor is very likely contributing meaningful information to the model. And you'll see this when we get to the multi-linear regression. You'll see how these numbers can differ based on the different variables. So here, the p-value is extremely small, so the area is statistically significant. Remember, it is statistically significant because that value is low. And finally, we have the lower 95%, upper 95%, which form the 95% confidence interval for the coefficient. This gives us a likely range for the true coefficient value. So in this example, the interval for area stays positive from um, from about 167 to 180. That supports the conclusion that area has a positive relationship with price. So if I summarize this output, I would say this. The simple regression model is statistically significant overall. And area is a statistically significant predictor, and the model explains a very large amount of variation in price. And that tells me this is a strong or a good simple regression model. So again, if I were to summarize this, After reporting my actual numbers, my R squared and my p-value, I would say something like, after I've reported the actual numbers, I would say something like, this regression model is statistically significant overall. Error is a statistically significant predictor, and the model explains a very large amount of variation in price. Um, well, let me change that. I don't really think this is a large amount in numbers. Let's use context here. But, I think it's a small variation. Um, and tells me this is a strong simple regression model. So remember, we're using our words. Now we do want to limit our descriptive words we use, stick to the data that we have. So the next thing I'm going to do though, I am going to skip into a multilinear regression model. So I'm going to go back to my training. Well, first I'm going to move this to the side because I want to organize my tabs. Next, I'm going to go back to my training data set and I'm going to build a multi-regression model. And to do that, I am going to go back to the training set here, and I'm going to go back to this data analysis tab. I'm going to do the same regression model. I'm going to click OK. For my, notice that these things are already populated from what I did before. So my predictor value, that's going to stay the same. That's everything in this A column. But our input, we're going to use multiple variables. So I'm going to delete this and I am going to select all of these variables here because these are the ones I want to be my predictors. So I selected all the data for all of the other valuables. So area, bedrooms, bathrooms, and stories. Labels is still selected. I'm going to name this one multi because I wanted to create in a new sheet. And then I'm going to click OK. And voila! We have a multi-regression model here. I'm going to clean it up a little bit so we can see what is here. Okay, so we're going to go through this just like we did the simple linear regression. And the first value we have is the multiple R. And this tells us again how strongly the model's predicted prices line up with the actual prices. Here we have about 0.994, so about 99%, which is extremely strong. That means the predicted values and actual values are lining up very closely. And next we have R squared. This is what we're going to be using for our comparison. And R squared again, it tells us how much variation. And ours is 0.09891, which is a very high number. Um, that is very high. So it explains about 98.91% of the variation in price. And now I'm going to look at the adjusted R squared, which is here. And I know we didn't go over all of these in the presentation, but they are useful in certain cases. For our case, right now, we're not going to be looking at everything for our analysis, but I do want you to know what these values are. Excuse me. So now let's look at the adjusted R squared, and this is important in multiple regression because this model uses several predictors. Adjusted R It helps us judge the model a little more carefully by taking the number of predictors into account. So here it's about 0.9985, which is still very high and very close to the R squared value. Um, it tells me that the added predictors are supporting the model well, instead of just inflating the fit. So then we have our standard error here. And this gives us a sense of the typical prediction area around the regression line. And here it's about 14,887. And it's one more sign that the multiple model is fitting the data better. And again, we had 70 observations in our training data set. So I'm not going to go over everything here, but notice that the significance here um, for our ANOVA section, um, let's see. We have, well, first we have this F value, and that's going to tell us about the overall strength of the model here. It's going to tell us about the overall strength of the model, and a larger F value usually means the model is explaining much more variation than what we would be expected from random noise. The value we care about most here, though, is the significance F. And this tells us whether the model is in as a whole is statistically significant. So here it's 4.09 to the negative 63, which is extremely small. That means overall the model is statistically significant. Now let's go to this coefficients table. And unlike our single model regression model, we have all of our variables listed here. And the first row is going to be the intercept. Um, we had this on the other one. And the intercept, that's the starting value when all the predictors equal 0. So again, in the real world, in your case, this may not be a realistic value of it being 0. So it's not something you would use as a business insight, but it's used for our prediction formula. So let's look at area. For area, the coefficient is about 174, and that means the area increases by 174. It means that when area increases by 1 unit, the predicted price increases by about $174. Okay? Kind of like when you're looking at a house and they have price per square feet, but that's where that number comes from. So this one, when we're selling our house and figuring out our price, we usually take the square footage, multiply it by this number, and that's how we get the price. So when you're looking at real estate and they're looking at price per square foot, this is what they're predicting. So now when you're looking at home sales, you're going to look at those numbers and think, "Ha, that's the coefficient of the square footage." Okay. So, and then we have, and this happens when the bedrooms, the bathrooms, and the stories, the other predictors are the same. The p-value here is what is really important. So it's extremely small, so it is significantly significant. And it tells us that area is contributing meaningful information to our model. If we're looking at the bedrooms here, Bedroom coefficient is about $9,182. That means adding one bedroom increases the predicted price by about $9,000. And that's when you hold the other predictors the same. So, and here the p-value, it's still small, so the bedrooms is significantly significant. Same thing with the bathrooms. The bathrooms, the coefficient is about 15,000. That means that for every bathroom that you add, the price increases about 15,000. And that's when the other predictors stay the same. And this p-value goes up. It's still small, but the p-value is still significantly it is significant. Then we have the number of stories in the house. As the number of stories goes up, the price goes up about $1,400. And the p-value is about 0.065, which is still small. Um, It's still below 0.05. You want this value to be below 0.05. And so the stories is still significantly significant. Now let's talk about the standard error column. For each coefficient, this tells us how much uncertainty there is around each coefficient. Smaller standard areas usually means that the estimate is more stable. And this is in regards to the amount. So the smaller the number, the more stable it is. So if we were to sort these, I would say error makes the biggest difference, and then the number of bathrooms, and then bedrooms. These numbers are close in context, so those would be the same for me if I were looking and judging this data. And then the stories would have less of an impact on the price. So, and the confidence intervals, those are pretty much the same. But if you look at stories, stories does have a negative number here, but we will look at that in a future presentation. Um, so if I were to summarize this output in plain language, I would say that this multi-regression model is statistically significant overall, okay? Because of this significance value here. It explains the variation in price, and all four predictors in this model are statistically significant. And by statistically significant, we mean that these values are below 0.05. Okay, I typed it. So for you guys who are visual, statistically significant means that the p-value is below 0.05. And if you look at it, this value here is to the negative 65. So it is way below 0.65, even though it looks like there's a 3 there. Same with these here. So these numbers are below 0.05. This means that this is a strong or good multiple regression model based on the training data. Make sure you include that based on the training data. Now, what are we going to do? The next thing we're going to do is we're going to use these. But the first thing we're going to do is we're going to copy some data. So I need my coefficients. I'm going to copy these from my multilinear. And I am going to, I just want to save it somewhere. I am going to do this on my validation tab. I'm going to put it here because I want to use these values later. So this is my multi. I can actually reference them in that, but I kind of want you guys to be able to see everything. So I am going to put it in here for me to use it. So this is my multilinear regression or multi-regression. Okay. And then from my simple regression, which I'm going to move over new. I'm going to take my multi-regression and move it over here. But for my simple regression, I'm going to take this one because I am going to be creating some values here. So we've created our models and ran our models. Now we're going to use our model to make some predictions in our validation data. So I'm going to put this here, and this is our simple regression, just so that we know what's there. All right. So now the first thing we're going to do is we're going to create our predictors on our sample data. So here, I'm going to use a pattern, and I'm going to take the coefficient. This is the equation we're going to use for our pattern. That's the equation we're going to use. We're going to have the area coefficient times the value that's in the area, and we're going to add that to the intercept value, which is here. And that's how we're going to calculate what the predicted price is. So that's our formula, right? So if I take this here and I were to actually put it into this G column here because I want it to be my um, simple prediction. And we're going to predict the price, okay? What I'm going to do is I'm going to use this equation. So actually, I'm just going to copy this equation and just fill in the blanks. So I'm going to take the area coefficient from my simple equation. So this is the area coefficient here. So I'm just going to copy this value. And in my equation, I'm going to paste it here. So B2, that's going to be the area row here. And then I need to replace the intercept value, which is going to be this value here. I actually want the actual value and not the cell. So I am going to escape this. And I'm going to come here and I am going to copy this full value. Come back to this equation and I am going to paste it in. And then I'm going to hit enter and it's going to fail because I didn't save this. So the area coefficient, let me figure that out and copy that one more time and replace it here. So notice it's my area coefficient times the value that's in the row. And then I add my intercept. And intercept is when the area is 0. So I hit enter and I get a price. So this is my predicted price. $341,745. In my mind, that's close to 358,000. Now to see all the predictions, I'm just going to fill that equation down, and I'm just going to double click this dot right here on the corner, the bottom right corner of my cell to fill it down. And voila, these are my predictions. So you can see the difference in the values. And this was the actual price, and this is my predicted price. So we've generated the predictions for the simple regression. Now we have to do it for the um, we have to do it for the multi-regression model. And our equation is, I have the formula here that I am going to do, and the formula is going to look for the multi-regression like this. So this would be you take the area coefficient plus times the value of the area, and and then you do add that to the bedroom times the value of the bedroom. You're going to add that to, you're going to take each one of your variables here, and you're going to multiply the coefficient by the value in that row. And then at the end, you're going to add the intercept, okay? So that's what we're going to do. And I am going to fill out this equation. So I'm going to copy it, and I am going to put it here. Okay, and I'm just going to fill out these values from here. So my area coefficient, I'm going to copy it and replace this. This is not a formula yet because there's spaces, and I didn't copy the whole value. So I am going to click here, and I am going to copy from here. And then I'm going to put that here as the area coefficient. The bedroom coefficient would be here. So I am going to copy that value, and I'm going to get the bedroom coefficient, which is here. And I'm going to do it for every variable that I have to calculate the price. So I have the bathrooms, which is here. I'm going to go here, and I'm going to replace the word bathrooms coefficient. And then I have the stories, which is here. And I'm going to put it in here. And the next thing I'm going to do is, so notice I'm taking the coefficient for each variable and multiplying it by the actual number in the row. And then I'm going to, at the end, I'm going to add it to the intercept value, which is here. All right, I have all of my numbers. Nope, I don't have all of my numbers yet. I have all of my numbers in here. I'm going to get rid of these spaces at the beginning. And now it turns into an actual formula. You can see that B2 is actually here. That's the area coefficient times the area plus the bedroom coefficient times the bedroom. The colors actually help. The bathroom coefficient times the bathroom value here. and the stories um, times the stories value here, plus the intercept coefficient. And I hit enter, and bam, that's my prediction, which is a little bit closer for this first value than the simple prediction. And I'm going to call this multi-prediction. Okay, now I'm going to fill this down and just take a look at the differences. Which values are actually closer? Is it the simple prediction or is it the multi-prediction? Just looking at the data for me, just eyeballing it, it looks to me like the multi-prediction values are coming out closer in my first few cases, not in all cases, but in my first few cases, than the simple prediction. So, but that's not how we compare our models. It's something we can look at and we do want to eyeball it, but we do want to look at the errors, okay? So, what we're going to do is next we're going to calculate our absolute errors. So, here we're going to um uh, let's see. I am going to remove my random column because I don't want to use that here. Let's see. Yeah, I don't want to use that here. And I want to make sure that my values are correct. Area equals, yeah. I'm going to take this and I'm going to delete this because I don't want you guys to think I'm using it for anything on this spreadsheet. So I'm going to delete that. Okay, so here I am going to have my simple absolute error. I'm going to actually name these columns so you guys can see my multi absolute error. I'm going to have my I'm going to calculate the squared error. I'm going to calculate the simple, the multi MAE, and I'm going to calculate the simple RMSE and the multi RMSE. Okay, so I'm going to calculate these values. And we're going to look at them all side by side to compare them. All right, so the simple absolute error, this is going to be the difference between this value and this value. What's the actual difference between what was done? We're going to do the absolute value because we don't care whether it's positive or negative. We just want to know the difference. So, for the simple one, what we're going to do is we're going to have an equation which is going to equal the absolute value, which is ABS. And I hit enter and nothing happened because we didn't put an equation here. Um, And it's going to be the price and minus the predicted price. Okay. And then I hit enter. And so it's this one minus this one. And it's off by 16,000. And I'm going to fill that down and you can see the differences in the price. Next thing I'm going to do is do the same thing for our predicted values for the our multi-regression model. So I'm going to take the absolute value of of our price minus our predicted value from our predictors, and we hit enter and we put it down. And if you're looking at the absolute errors, the smaller number here is going to be the better version. And as I'm looking at these, you see that some cases, um, the absolute is smaller, some is bigger. So in these cases, for this one and this one and this one, the multi is better. But for this one, the multi is worse. And for this one was way off. So it's there, you're gonna see some discrepancies, but we're gonna look at the big picture, the whole picture. So let's look at the squared errors, okay? So if we look at the squared errors, this is the absolute error, it's going to tell us how far off the prediction is from the actual value. And we're not worried about, whether the model is too high or too low yet, but you can look at the differences and see the differences in the numbers. But next, we're going to calculate the squared error. And this is where we take the differences and we square it. So for the simple squared error, it's going to equal, and we're going to take our price, and we're going to subtract our predicted value, okay? And then we're going to square it, okay? And then I hit enter, and you get a value. I'm going to do the same thing for this other column. And for our multi-regression model, I'm going to the squared here. I just pasted in the value of it, and I am going to fill the values down. And these columns show squared error. Squaring the areas makes larger misses count more heavily. It's important because for RMSE, it's designed to react stronger when the model has bigger mistakes. So I'm not going to focus on these numbers quite yet. Next thing we're going to do is we're going to calculate the MAE. And to do that, we're going to have you're going to do the MAE. That's just going to be one value. It's for the full model, the mean absolute error. So I'm just going to average the absolute error of everything. So for the simple model, I am going to have it equal the average of all of the values that are in our simple absolute error column. Okay, so this is our mean absolute error for our simple model. And then I'm going to do the same thing for the multiple. I'm going to take the average of our multi-absolute error here. And I just have one value. Now notice this is for the whole model, so I don't have to fill that down. These are the values. And notice that the multi, and I'm going to actually spell that correctly. Um, the multi mean absolute error is actually smaller for the mean absolute error is smaller for our multi-model. Next, I'm going to calculate the RMSE, our root mean squared error. So I am going to um, take the square root, which is equals SQR. I'm going to take the square root of our multi-absolute error. So where am I? Where am I? Where am I? Supposed to be the simple. No, 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 no. Here, of our simple squared error, okay? I'm going to take the absolute value, the square root of this. Sorry. I am going to take the square root of the average. Simple squared error, which is this. And I'm going to close that, and I'm going to close that, and hit enter. And that is our RMSE for our simple. Now for our multi, I am going to do the same thing, but I have the equation I'm going to put in, but it is, I am going to take the square root of the average of our multi-squared error. And this is our RMSE. Now, so I'm going to make this so you can see it a little bit better. I'm going to copy these values and I am going to compare these models, okay? So I'm going to create a new tab for my comparison. I'm going to type correctly. And here I am going to put my values somewhere else because I'm going to paste them in. But I'm going to paste in the values. I didn't copy it. Go back to our validation. I'm going to copy these. And in my comparison, I am going to paste them here because I am going to use them. And I'm going to right click and I am going to paste the values because I want the values. And the next thing I'm going to do is I'm going to go to my simple regression model. I'm going to copy the R squared and I am going to bring it here into my value comparison. And this is my simple. I'm just copying it so that I can organize it. Didn't copy. All right. And multi. I'm going to copy the R squared from my multi regression model into my comparison. I'm going to make it look good. So I am going to have my models here. So I'll have the simple model. I have my multi-regression. And then I am going to compare the values. So I have my MAE. Nope, I'm going to start with R squared. I have my MAE. And I have my RMSE. So I'm just going to populate these where they need to be populated. So this is my simple MAE. This is my multi-MAE. And this one is my simple RMSE. These can be copied together because they are in the same order. You're going to put those here. And then I have my simple R squared. And then I have my multi-R squared. Now, so I have my three metrics that we're going to look at here. We have the simple regression, the multi-regression model, and then we have the R squared, the mean average. We have our RMSE and our MAE. So we are going to figure out which ones are better. The mean absolute error, and we have our root mean squared error. So what are we going to do? Remember, for R2, we're looking for here. For R2, take the higher. For MAE, take the lower. And I'm going to say model because that's what we're going to do to choose. And same thing for RMSE. Take the lower. Okay. So this is by how to choose column, just so you can see what I'm doing. So for R2, we have our multi-regression that has the higher R2 value. So I am going to say put multi-regression because that one has the higher value here. And then for the MAE, I'm going to take the lower value. So which one has the lower? I'm going to name this choice. Which one has the lower choice? It is the multi-regression. And for the RMSE, the root mean squared value, take the lower model. And it is multi. So in this one, we have a clear choice on which model is better. So to summarize, I am going to use the multi-regression model because it has the best predictors because it has a lower R2 squared value. I mean, it has a higher. You want the R squared to be higher. I'm going to choose a multi-regression because well, okay, if you were writing this out, I would say something like the values for the simple regression R2 was this, the value for the multi-regression R2 is this, the value for the MAE is this, the value for the multi is this, or use this chart, include this chart in your analysis. Um, and then you can explain it. Because the R2 is lower, the the mean absolute error, MAE, is I'm going to say this a little bit better. Because the R2 is higher and the mean absolute error is lower and the RMSE is lower for multi-regression 2, I am going to choose multi-regression model 2. And that is how we compare our models. Now, this was a clean example, but sometimes you have to, these may not be the same. And then you have to look at your business case, your problem, and figure out what's most important. And in your analysis, say why you chose the model that you chose. If accuracy is most important, and you want to use this one. But if something else is important, you want to look at these values. Like, for example, if you have some outliers that are really, really huge and those big misses are critical, you may want to choose something where the RMSE is lower if your MAE is higher. So you want to use these, but it's not absolute on what you choose for your model. You kind of have to think about it and justify your choice. Document your decisions that you make along the way. Okay? So this is your evidence that you'll use. You compare your R square and it tells you how much variation there is in price. And then you compare the MAEs and it tells which model is off by less on average. And then you compare your RMSE and that tells you which model handles the largest misses better. And the recommendation is going to be both based on all three. A model with the higher R squared and lower MAE and a lower RMSE usually gives you the better overall evidence, okay? So make your choice based on that. So we just went through the full process. I don't know where my presentation went. We just went through the full process and we let's see. We randomized the data. We created sample data with the 100 rows. We split our data um, into our training set and our validation set. We built a simple regression model and a multi-regression model. We looked through the summary output and went into details of what it means. We used the coefficients from that summary output to create our predictions. And then we calculated our MAE and our RMSE on our validation data. Then we compared the evidence and recommended which model was the best. So that was our full workflow on how we evaluate our predictive models. So yeah, that's what we work through. So key takeaway, you're gonna have your sample and to summarize, we have our sample, we split our data, we build our models, we test them on our validation data. We use the multiple metrics, the R squared, the MAE, the RMSE to evaluate the performance of our metric. And we choose the model that's the best fit based on our evidence and the purpose of our um, model. So, thank you so much for watching today, and I hope you have a better understanding of how predictive models work.